We're going to be spending the whole first part of our calculus study finding derivatives. So before we start, we want to talk about and understand when can we not expect to find the derivative of a function. So if we know when we won't be able to find a derivative, we won't get stuck looking for a derivative when it's not there. So remember, what is a derivative? Derivative means the slope of a function. So these four different scenarios in which we would not be able to find a derivative, 3 of them are because we wouldn't be able to figure out what the slope is. So that first time you're going to draw in a picture of each of these 4 possibilities on your notes paper. The first situation is a graph like this one here that has a corner. And here's what makes a corner, really, when you think about it. That piece of the function is a line, just happens to be a line, and its slope is negative. If that were the function y equals the absolute value of x, then the slope of that piece for which x is less than 0 is negative 1. This piece of the function goes uphill. In this case, if this were f of x equals the absolute value of x, the slope of this piece is positive 1. So the question here is, what's the slope of the graph when x equals 0? Because if you were coming along the left piece, the slope was negative 1. If you're trying to come along the right piece, the slope is positive 1. So here's our first problem. My slope from one direction is one number, my slope from the other direction is another number. And since a derivative is a limit, my limits from the two sides don't match, you will not be able to find the derivative of a function at a place where there is a corner on its graph. This next one here on the right, a cusp, it's just sort of a fancier version of a corner. But notice here the slope coming from the left is negative because my function's going downhill. Slope coming from the right must have been positive because the function goes uphill. You won't be able to find the derivative of a function at a place where it has a cusp. Now maybe you've never seen a cusp before. They occur when you want to raise x to a rational exponent, so raise x to an exponent that's a fraction, and the numerator is even and the denominator is odd. So that's where you're going to see a cusp. A vertical tangent, so imagine this guy right about here. If I try to draw in the tangent line, it's going to be vertical. Well, derivative is slope, and the slope of a vertical line is undefined. So anywhere you have a tangent line that would have been vertical, we say that the slope is undefined, so the derivative is undefined. So those are the 3 cases where we're not going to be, 3 of the 4 cases where we won't be able to find the derivative. This last one, this is why we talked about continuity so much in chapter 2. I'm still going to keep asking you about continuity. I cannot find the derivative of a function any place where that function is discontinuous. So here I have a discontinuity. This happens to be a jump discontinuity. I will not be able to find the derivative here. So I have a place for you on your paper to answer this challenge question. Which one function in your functions booklet has a point on its graph, a point in its domain at which there's no derivative, at which the function is not differentiable? Here's a hint. It's not tangent. Tangent has some places where there are discontinuities, right, where the function skips over those vertical asymptotes, so x equals pi over 2 plus k pi. But they don't count because those x values are not in the domain. So it doesn't count to say the function's not differentiable there because the function wasn't even graphable there. So see if you can find a function, flip through your function booklet, see if you can find a function that does have a point on its graph, but at that one point, you won't be able to find a derivative. So now we have our informal definition of when a function is differentiable. It has to be continuous and it has to be smooth. So a function is differentiable any place that it is continuous and smooth is our informal definition. Most of the functions we study will be differentiable, or we'll have to make them differentiable before we study them. And now what we want is a formal definition for when a function is differentiable. Remember, the derivative is a limit. A limit as you let that h value get close, the h value gets smaller as you let 2 points on the graph. So the slope of the secant line, let those 2 points get closer and closer and closer until they're essentially right on top of each other. So this is our formal definition. Really what it says is for a function to be differentiable, its derivative from the left must equal the derivative from the right. And you'll notice here the, sort of that alternate form of the derivative that we've been using, that we started using in 3.1. So the limit as x approaches c from the left of f of x minus f of c over x minus c has to equal the limit as x approaches c from the right of f of x minus c, f of x minus f of c over x minus c. This has a place on your blue paper, on your green paper, so write it in.